Hi, everybody. My name is Haji-Akbari. I'm an assistant professor of chemical and environmental engineering at Yale. And today I'll be talking about using advanced sampling techniques to study solute and ion transport through semi-permeable membranes, which have a lot of applications in many disciplines. Uh, they're used a lot in chemical separation processes such as desalination and gas separation. We use them a lot these days in the form of these N95 masks to avoid COVID infection. And they are also an important part of biological cells and organelles and modulate the transport of small molecules, ions, and macromolecules in biological systems. And what makes the membranes useful is their selectivity, or the fact that they can selectively exclude certain types of molecules or ions while letting through others. And membrane selectivity at the molecular level is a complex arises because of a complex interplay between steric effects, or the relative sizes of molecules or ions that try to pass the membrane, versus the sizes of pores or cavities within that membrane, and also electrostatic effects, such as charge properties of those membranes, as well as solvation effects, or the amount of energy that has to be spent to partially desolvate the molecules before they enter the pores and cavities within the membrane. And because of this complexity, there has been a lot of interest in using molecular simulations to study membrane selectivity. There are, however, many challenges in doing so. And you're sort of familiar with the first challenge, which is true for any rare event, and that is the issue of inaccessible timescales. Because if you have a selective membrane, the mean first passage times for ions or solutes passing through that membrane will be very long. And if that time exceeds a few microseconds, then determining it accurately will require tens to hundreds of microseconds of MD trajectories, which is towards the upper practical limit of what we can simulate these days for most systems. But there are two other issues or challenges that are specific to membrane separation processes. First of all, these processes are usually non-equilibrium, and they are driven either by a pressure gradient or electric field. So you can't therefore use all sorts of methods that are suitable for studying equilibrium rare events like umbrella sampling or transition path sampling. So you have to use specific systems that are compatible with irreversibility. And the third issue is that uh, when we are studying a membrane separation processes, we are dealing with two or more reservoirs that are separated by a membrane. And these reservoirs are technically open systems. And if you have a truly selective membrane, the number of molecules within these reservoirs can change considerably. So you can have significant changes in concentration, and that will uh, that will basically prevent us from reliably determining the uh, selectivity and passage times as a function of concentration or feed concentration, which is a process variable that we are typically given in designing membrane-based processes. So in recent years, in my group, we have been using forward flood sampling to study membrane separation, and forward flood sampling actually is suitable not only for accessing really long timescales, but it can be used with non-equilibrium integrators. And also because of the way that it works, it results in minimal changes in concentration within reservoirs, as we will discuss. So let's say you have a membrane with a single pore that separates two reservoirs. And in each reservoir, you have a four-component solution comprised of these blue, red, purple, and green molecules. Um, and then and we specify the state of the system, which we some have a stable in. Here we don't have equilibrium, so metastability is a loose term, but we specify this of the system the number of molecules of each that exists in one of the boards. Now here we form the filter. So we have one blue, red, purple, and green. State of the system will be noted as F116. And we are particularly interested in select membrane. So pore that I have here, you will assume that this pore only allows for the passage of one solid at a time. So the number of solids on each side can change by plus or minus one during each transition. And that basically limits the types of transitions that we can study. So one possible transition is when the next blue molecule or ion passes the pore. So we go from F116 to F262. But we can think other type more general transitions. So we can think of a transition in which one of the molecules on left-hand side go to the right sides, which will correspond to this particular transition because the solute can either type. Now, in order to study each of the transitions with an order parameter or at some simulations, so the parameter will be based on a curve to distance from the mouth, so it will be the function on this L that basically is negative in the and it increases continually along the row. And then the order parameter basically a curve to the distance of suitable solute that is in the membrane. So for example, for the first transition, it will be the second largest curve directed distance for the blue molecules because the first blue molecule is already on the right hand side, so its value is very positive. And in principle, it can think of suitable Persian coordinates or corrected distance for more complicated or geometries and topologies you can see here. After fixing the order parameter and we use for sampling to determine transition rate of going from to B, which are one of these states we specified in the transitions. And this the transition rate is determined by recursively calculating the trajectories that start from our starting bin and reach each of milestones which level set of the parameter. We start with configuration in the starting basin and we explore the starting basin using non-equilibrium trajectories. We monitor for first crossings of lambda 0, and the number of these crossings per unit time gives us the flux of trajectories that start in A and reach lambda naught. Then we get a bunch of configurations there, and we then determine the probability of going from lambda 0 to lambda 1 through an FFS iterator. So from each configuration, you start multiple trajectories, and you terminate them when they reach the next milestone or they get back to the basin. And the fraction of successful ones will give you the transition probability of going from 0 to 1. And we continue this process over by passing along these second batch of configurations to the next iterator. And by doing that all the way towards the end, and by combining these transition probabilities and the initial flux, we get the overall flux or rate. And so we recently used this method to study ion transport, sodium and chloride transport through a nanoporous graphitic membrane. I talked about this work in detail last year, where I most discussed the physics of transport and what we can learn about it. Today I want to emphasize on some more peculiar methodological aspects of these calculations and advantages it has. So to sum up, we have a three-layer graphitic membrane with a cyanometer core, passive with hydrogen atoms, and we have these two yellow pistons. On the left side, therefore, we have a sodium chloride solution, and then we have pure water right-hand side. And by applying the hydrostatic pressure, we drive the transport of solvent solute through the network. Now, transition interest to us was basically the transition from F0 union of 01 F10, which is basically the time scale they needed for the first ion, whether it's a sodium or chloride, to pass through the pore. Now, during the and so first of all, I want to emphasize that during the basin exploration stage of this calculation, we can get really accurate information about the transport of water molecules. So here I'm showing the histogram of the number of water molecules that pass the membrane over 5 nanosecond windows within these basin exploration simulates. And you see there is a lot of variability by proper averaging, get a good sense of the passage for water molecules. So we need to conduct separate calculations for water mobility. They naturally emerge from our first calculation by looking at the parking base. Now we can the iteration of FFS being successive milestones. Here I'm showing the cumulative probability plot as a function of distance per mile or the order parameter, and you set this plot actually saturates to this final value, and that's when the ion is the membrane. This shaded region is basically the interior of the pore. And from these probabilities, we can get the solute passage times. As you can see here, they are in the order of microseconds. And even though we didn't distinguish or discriminate between sodiums and chlorides, we observed the first ion past the membrane is also chloride. So this is something comes naturally comes out of the calculation without making any assumptions about ion as the pore. Now, if you look at the computational of this calculation, I'm showing the total length of each trajectories. LNG trajectories conducted for each temperature, and you note that these are in the order of a few microseconds. To determine these microsecond scale transition time scales, which is extremely efficient, because if you wanted to calculate these passage times using conventional MD with this level of statistical precision, you would have needed tens to hundreds of microseconds of MD trajectories, while here we are using only a fraction. And indeed, if you look at the transition in which the first sodium passes the pore after a chloride has already passed the pore, the transition time scale increases a lot. It increases by around 2 orders of magnitude. But we determine this almost millisecond scale time scale with 17 microseconds of trial trajectories, which is only a fraction of the actual transition time. And indeed, here you can see the computational cost of conducting an FFS calculation as a function of mean ionic passage time. So these are for the calculations that I discussed and some other calculations that we have conducted in my group. And you see that there is a decent logarithmic scaling between the two, which means that you can estimate arbitrarily long passage times with a reasonable amount of computational cost using FFS. Now I would like to briefly discuss the third issue that I mentioned earlier, and that is the issue of concentration. So I will be focusing on this one data point at 300 Kelvin. The water transport time scale is in the order of 0.3 nanosecond, while for chloride, the passage time is around 2.6 microseconds, which means that for every chloride that passes the pore, 7,900 water molecules would have done so. So if you wanted to observe this chloride transport process using regular MD, the number of water molecules in your reservoirs will change considerably during this observation time. But that doesn't happen in FFS, because in FFS we are combining a large number of short trajectories, and during each of those short trajectories, the number of water molecules in the reservoirs doesn't change that much. So here I'm showing you the histogram, a number of waters in the feed as a function of the order parameter. And you see that the histogram barely changes and the averages don't change either. And throughout the entire process, we have a change of around 5 water molecules out of 3,300 water molecules on the left-hand side, which is a very small change, which means that the selectivities and passage times that we are reporting here are essentially computed at a constant chemical potential of water molecules in the left-hand side reservoir. So in conclusion, four-flood sampling provides an efficient and scalable framework for computing arbitrary long ionic and solid passage times. And it is not only efficient, but it's suitable for studying non-equilibrium transport. And also it maintains the chemical potential in the two reservoirs, obviously except for the traversing solids. So with this, I would conclude and I would take any